Uranium is a fissile material. This means that under the right conditions you can cause the large nucleus to split into smaller ones, producing an awful lot of energy. In this video I set out to explain how this dangerous reaction can be controlled and how it produces the enormous amounts of energy that it definitely does. Well, come along physics fans. You may be surprised to learn that in one sense a nuclear fission reactor is a pretty straightforward beast. At its basic, what you need is a number of rods of purified uranium and a big bath of water. Additionally, you're probably going to want some control rods which can be lowered in and out between the rods of uranium. We'll talk more about those later. Our first job is to generate the equation for a uranium nucleus as it undergoes fission. So let's get straight on with it. We start off with a 235 uranium nucleus at which we fire a slow moving or thermal neutron. If all goes well, this neutron will be absorbed into the uranium-235, creating an unstable 236. The 236 nucleus will then decay into two daughter nuclei. If you add up the mass numbers on the left and right hand side of this equation, you'll see that we are 3 short, and this indicates to us the number of neutrons that are produced. A significant amount of energy is also released as electromagnetic radiation. The fission process is kicked off by having what's known as a thermal neutron, in other words, one that has low energy, the kind of energy is associated by heating things. This means that it's not moving very fast, which in turn means that the uranium nucleus can absorb it. The nucleus of uranium becomes very unstable when it absorbs the extra neutron. This means that it will split, producing a number of neutrons in the process, in this case 3. These 3 neutrons might be expected to just go off and fuse with some other uranium nuclei that are hanging around, but this doesn't happen because these emitted neutrons have a lot of energy. In other words, we need to slow them down, and this is done by the water, or the moderator as it's more properly known, that surrounds the rods. The moderator can be made of different materials, but we'll just work with water for the moment. Considering the collision that's going to occur between a fast-moving neutron and a water molecule, you need to notice that, roughly speaking, more or less, the mass of a neutron isn't that different from the mass of a water molecule. This means that there is a good spread of kinetic energy in the collision. In other words, energy will be transferred from the fast-moving neutron to the water particle. Imagine what would happen if a very heavy ball, a big ball, hits a very small ball. In this case, what happens is that the big ball just carries on moving and probably the small one shoots off too. In other words, you haven't removed much energy from the big ball. A better situation occurs if you have 2 equal sized balls. Consider 2 snooker balls, for example. As they hit, they both move off. The energy is shared between them. And this is how the moderator works. The fast moving neutron will undergo several collisions so that it's moving slowly enough to now interact with another uranium nucleus. So the moderator's job is to slow down the fast moving neutrons, meaning that we can get a chain reaction happening. The control rods are used to control the rate of nuclear fission reactions that are happening. In other words, how many of them are happening in, say, a second. This is because they're constructed of a material like boron, which is actually extremely good at absorbing neutrons, not slowing them down, absorbing them. This in turn means that if you lower the boron down between the nuclear fuel rods, they're going to absorb the neutrons that are on their way to create other fission reactions in the next rod, therefore reducing the rate of reactions. In a dangerous situation, such as the ones Homer Simpson was always experiencing, you would simply push the control rods as far down between the nuclear fuel rods as you could, turn around and run like heck. The energy released in a nuclear fission reaction comes from the fact that the mass of the reactants is greater than the mass of the products. In other words, you lose, albeit a small amount of mass for each reaction. Up to this point, you probably think that the mass of a proton is the same as the mass of a neutron. However, if you measure masses really carefully, like to 4 or 5 or 6 significant figures, you'll see that the mass of a neutron is not the same as the mass of a proton, and the mass of a proton can change depending on what its circumstances are. And this explains why it is that there's a mass loss going from the left-hand side to the right-hand side. Let's work it out for this example. To do this, we're going to use the super accurate atomic mass unit, All of these values of mass then are measured in U. So we add the mass of one neutron to the mass of one uranium nucleus. On the right hand side we add together the masses of one barium nucleus to one krypton nucleus, and then we have to add in the mass of 3 neutrons. Now, by taking away the before and after masses from each other, we can work out the mass loss in each interaction. Of course, this value will be in U, so to get it into kilograms we need to multiply it by the value of U. Now we can use everybody's favourite equation and multiply this mass loss by c squared in order to obtain the value of energy in joules. So this is the energy released during one interaction, and on one level you might think to yourself, well, that's not very much, and I guess it isn't. But if you consider the absolutely gigantic number of uranium nuclei that you have in each rod available to react, you can quickly see that this energy very soon mounts up into something very significant. If you found that video interesting, why not try this one?